Okay, so welcome. Can you see me? Can you hear me?
Yes, we can.
Okay, so let me. So my name is Chava, and let me show you a few slides about a new quantum engineering master program, which is actually one of the very few such programs in Europe or in the world. So let me start with the most important slide. When you want to come here, what is the purpose of this program? So basically, this program is for you if you like physics, but you don't want to be a physicist, you don't want to do very theoretical or research type of work, but you would like to have something that is much more problem-oriented or application-oriented, but still needs a lot of physics and to need a lot of such background. So the idea is basically that we are going to learn a lot of physics, math, scientific programming, neural network, modern electronics, modern photonics, theory of computing, but we are not going to learn it for the sake of theory, but really we are going to focus on potential applications that can be done by modern physics and that can be done by quantum engineering and quantum science. So next slide, please. Okay, yes, so just let me show you just one slide that what is quantum engineering. So if you learn physics or science in an engineering curriculum today, even if your curriculum is very good in giving you this knowledge, basically all that you learn, or most what you learn, is basically 19th century physics. So all the physics, mechanics, electrodynamics is basically, even if it's very deep knowledge, basically most of what you learn ends at the end of the 19th century. And basically there is a lot that happened in physics since, and the future is, and the expectation of most people on the field is that to do state-of-art engineering, you're basically going to need more and more to understand modern physics, to understand quantum science, because these fields are going to enter basically the engineering toolbox very, very soon, in probably in the next 5-10 years, but certainly during your career in the next decades. So basically, one of the primary goals is this program to give you a knowledge that keeps you in the game for the next decades, that gives you all the foundation and knowledge to be able to do and work an application and engineering programs that require you to knowledge of quantum physics or modern physics in general. So next slide, please. Okay. Oh yes. The core of the curriculum basically summarized on this slide. Since we want to build the master's program around applications and learning all the physics and mathematics and soft skills that belong to these applications, there are basically 2 or 3 focus areas in this master's program. So one focus area is basically quantum sensors and quantum limited measurements, which are a very, very hot and very important field. Basically, the idea is that anytime you want to do sensitive measurements, either physics measurements or measurements with medical devices, you really have to understand the operation of your sensors. And if you really want to go to the ultimate limit of sensitivity with a sensor, you really have to understand the quantum mechanics of these sensors. There are actually a lot of quantum sensors already on the market. So in instruments you can buy, nitrogen vacancy centers are the most well-known among them, but there are basically a lot of different type of quantum sensor applications, and basically learning about them, learning the physics of them, possibly trying them also in the lab is one of the goals of this program. The other focus area of the program is what is actually the biggest field or biggest subfield of quantum is basically quantum computing and quantum algorithms. So probably most of you know that basically quantum computers and quantum algorithms are the ones that promise you an exponential speed up in computational problems that would be impossible to solve by classical computers. There are no practical and working quantum computers in the world, but there are basically experimental quantum computers. There are quantum computers you can even try and play with online. Using these quantum computers requires very different type of programming skills that you would have with normal computers, and of course they require you to understand the underlying physics and to understand that what are the really difficult applications that this quantum computer can be used to. So basically, learning about those things and is another focus area of this master's program. And of course, we try to keep our eyes open for all the modern stuff like quantum biology, quantum energy, and all sorts of things that are emerging in modern applications. So next slide, please. Is it? Yes, the one idea behind the program is that, of course, the quantum science and the quantum engineering is at the core of it. But basically, we'd like to keep you different paths open, different pathways also to open, basically where you're in, depending on where your interests lie. So it would be possible to take some classes that take you deeper into the theory or give you a deeper physics knowledge than the standard part of the curriculum. We also try to show you some laboratory techniques, electronics measurement techniques, where the idea is basically that you gain some experience which are usable not only on quantum systems, but in general with electrical measurements or laboratory techniques. A large part of the curriculum is about theory of computing, non-Boolean computing, neuromorphic computing, different models of computing, again, analog computing or for example, physics-informed AI devices. So basically, if you take the program, but you at the end, you are going to do purely software engineering, you are probably going to be able to use much of this knowledge that are not special to quantum, but the new type of computing algorithms. And of course, another important part of the curriculum is that we would like to, part of the curriculum is some microelectronics knowledge. Basically, microelectronics is also based on quantum science and quantum technology, even if to do it in the everyday engineering experience, you don't have to do the details of quantum mechanics. But we have some microelectronics components in the curriculum also. Please, next slide. And this is just to mention basically that besides quantum, basically, if you would like to plan working on microelectronics, there's a huge microelectronic renaissance in the world. You know, probably that chips are probably the most important technologies of the 20th century. Every country is trying to have its own chip manufacturing, not depending on others, have the knowledge in-house or in the country. So there are new fabs being built on the world everywhere. So what we see basically that in the next few years, there's going to be really a big need of engineers who understand modern electronic devices, quantum devices, and more conventional solid-state devices. And our plan in this program is to basically prepare you also for this microelectronics renaissance, and that you are able to do really this highly qualified microelectronic related tasks. Next slide, please. And I think this is the last slide, so we can just give you the overview of the program. So what are the main tasks of the program? So we have a theory of computing task where we are going to mostly talk about unconventional computing, quantum algorithms, neuromorphic computing, AI. So there's a lot of knowledge usable beyond quantum. We have a class that is mostly quantum computer programming, so not the quantum physics, but more like the quantum, the practical side of how to program quantum computer, how to exploit or take advantage of the advantage of quantum processes. Of course, we have a strong mathematics and physics background. many people with very different education. So basically, many people will come to this program who come from very different background in mathematics or physics. So we try to bring everyone to the same high level and have the necessary mathematics and physics courses. There are going to be courses in nanoelectronics, microelectronics, which is not really which is might not be necessarily quantum. This is something that are skills that you need to understand quantum devices, how they are fabricated, how they are made, how they are interfaced to normal devices. And of course, there are going to be some laboratories connected to sensors, measurements. So basically to give you all the practical knowledge that for quantum circuits or microelectronic circuits, you're able to measure, understand issues with the measurement and how to deal with these devices. So basically that was a short overview, and then we started basically this master's program this semester. So the second semester is coming up now. So it's all very new, but very exciting, and we hope to see you or some of you here next year. That was all from my side.
Thank you very much, Professor Csaba. And actually, I think, as far as I know, that you have to leave to attend another meeting right now. So
it should be okay for me to stay 10 more minutes or so.
Okay, then let's see the questions. We have a question. I will read it out. I'm recently working on quantum entanglement and its application on continuous variable system using Duans and Simon criteria. Is there any chance to get admission or direct contact with the teachers?
Yes. So yeah, welcome to write an email, and then so if you so let me say so from what you write, what I understand is that it's a fairly so your expertise lies really in quantum computing. So or the quantum engineering program is a bit broader than that, but certainly quantum computing is a very important part. So please write to me, and I'm very happy to share more details with you that what we teach here, or what would be opportunities for you to get in touch with us, possibly even talk about some problems or physics before you come here. So yeah, welcome to write an email.
Yes, we will give the participant who is asking the email address. Okay.
Okay, I will write it.
Yes. One more question. What kind of architecture is focused on here? For example, superconducting.
Yes. We try to teach about all of them and give the physical foundations of everything. So one thing I must admit, and this is some shortcoming of the problem. For example, we don't have big laboratory equipment on quantum computing. So, for example, we don't have a cryostat, we don't have superconducting laboratory. So, what we focus in more like the theory, the modeling part, the quantum algorithms, and basically the ways to use quantum computing. We have collaborations with other universities, with TU Munich, Torino. So you can have access to experimental facilities, but not in-house. So the short answer is basically that we don't have a focus on any technologies or superconducting technologies. It's more like a broad program to give you an introduction into every ways of doing quantum computing.